Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, welcome everyone. It's my pleasure to have Jason Hartline speak today. Jason is no stranger to the area. He graduated from University of Washington under the guidance of Anna Carlin, and he was also a researcher at the Silicon Valley lab, and currently he's a professor at Northwestern University. He's going to talk about approximation and mechanism design.
Thanks, Nikhil. Good. So this is going to be a survey talk. I'm going to talk mostly about 3 papers. I think that the time right now is a very nice time for mechanism design in computer science because there have been a lot of things coming together, and the way I think about things now is totally different from how I thought about it 2 years ago, and I think that's a good thing. And so these are some of the papers that helped me think about things differently. And the last one isn't even mine. I wish it was. It's a great paper. It's one of Tim's and his students' papers. So anyway, so I'm going to talk about sort of how I think about mechanism design now and draw results mostly from these 3 papers, but also there'll be some other results I'll reference. So mechanism design is, in general, asking the following question: how can a social planner or optimizer achieve a desired objective when the participants of the system that the social planner is trying to design for have private preferences, and these participants are selfish and they may manipulate their preferences to try to get a better outcome for themselves. And I'm a theoretician, so I do mechanism design theory, which tries to do the following 3 things. I would like the theory of mechanism design to be descriptive, meaning you take your theory and you say, oh, what does theory predict? And then you look about what happens in real life, and you hope that similar kinds of things happen in real life, and you say, oh, well, my theory predicted what happens in real life. You'd like it to be prescriptive in the sense that maybe someone wants you to design a mechanism for some situation that no one's designed a mechanism before, and you want to be able to take the theory and use that theory to figure out what to do in this new setting that we've never talked about before. And the last thing is something I think is especially important. You want it to be conclusive. You want to be able to sort of pinpoint salient features of good mechanisms or salient features of the model that you're designing for that are really important to really get right. Okay, so you want to do these 3 things. The informal thesis I have in this talk is that approximate optimality often can do these 3 things very nicely, and it even does them very nicely in cases where exact optimality fails to do some of these things. Okay, so this talk, I think, really motivates why I care about approximation and what kinds of approximations I care about, because I care about approximations to do these 3 things. Okay, so I'm going to start with an example problem, which is going to be both motivational in terms of techniques, and it's going to be I'm going to use it as later in the talk to actually show the theorems about auctions. Okay, so a gambler is playing the following game. Okay, there's a we have the following optimization problem. There are a sequence of n games. Okay, and each game has a prize. And the prize for game I is drawn from some distribution. And the gambler knows these distributions exactly. And the gambler gets to play these games as follows. In the first day, he plays the first game, he realizes the first prize, he draws it from the distribution, and he has to choose whether he wants to keep this prize and quit playing the game, or discard the prize and go on to the next day. Okay, and so on day I, he draws prize I from the distribution, and he gets to choose to keep that prize and go home, or give up the prize and continue on to the next day. So it's a question of when should this gambler stop? Okay? Good. So how should our gambler play? And in this talk, I'm going to sort of pose a problem, talk about what's optimal, and then show how approximation says some perhaps a lot nicer things about what we should be thinking about doing. Okay, so here's an optimal strategy. I'm going to pick a threshold Ti for each stage. And in the stage I, if the prize is above this threshold, I stop. Okay, and I'm going to solve for these thresholds with backwards induction. Right, because on the last day, my threshold should be 0. I take any prize I get.
So what's your criteria for optimality?
The gambler is trying to stop with a prize that's good, so he wants to maximize his expected prize. Okay, so he gets some prize, so he's supposedly risk neutral, so it's expected maximum, the expected value of the prize he gets, he's trying to maximize. Okay, so on the last day, I haven't quit so far, I draw a prize from distribution, it's got some value, I should take it. Right? Clearly. Good. So on the second to last day, I can calculate the expected value I would have had on the last day. And I should take this prize only if its value is above the expected value on the last day. Right? So, and then on the third to last day, well, I know what the expected prize I would get from the second and the last day is, and so my thresholds are increasing in each day as we go backwards in time, right? And I have thresholds solved by backwards induction. Good. So let's discuss. This is optimal. Let's discuss this optimal strategy. It's complicated. I have n different, mostly unrelated thresholds. They're going to be increasing as time goes on, decreasing as time goes on. I have a hard time making general conclusions about what good strategies are, besides that there are these thresholds and that they decrease as time goes on. There's a question?
Yes, is backward induction the same as dynamic programming?
Yes. It's not very robust in the following sense. Let's suppose that I swap the order of two of the games. Then everything changes. I have to redo my entire calculation from the latest prize to the beginning, right? Or what if I made a change to the distribution strictly above one threshold or strictly below a threshold? Things change. Okay? And it's not very general in the sense that I don't learn too much about changes to this game, like the things that follow a similar kind of high-level idea. They're prizes, trying to get a good prize, etc. We don't learn too much. Good. So optimal strategies give great performance, but they don't do too much in terms of insight and understanding and generality and robustness and all these things we might like. So I'm going to go to non-optimal strategies. I'm going to consider approximations that simple approximations this gambler could try to go for. And the simplest thing you could think of is let's just have a single threshold strategy. I fix in advance a number t. And I'm going to play each game in order, and the first game whose value is above t, I take that prize and quit. That's my game. This is obviously not optimal. Even on the very last day, the prize is below t, I don't take it. Okay? That's the strategy I'm talking about. Okay, so here's the theorem about such a strategy. The theorem is that if I choose t carefully such that the probability that on the last day I still don't even take a prize and I get no prize. If I choose t such that the probability that event is exactly 1/2, then the expected value the gambler gets for playing this threshold strategy is at least the expected maximum value over 2.
Here you are assuming FIs could change again. FIs are different for this theorem.
So the problem setting, these FIs may be different for different games.
Mm-hmm.
Okay?
That's true for the theorem also.
That's true for the theorem also.
Okay.
It's the same setting. Okay, so I want to note that actually this is an upper bound on the optimal strategy, right? This is clearly, you'd love to get this, but you can't because you don't have foresight. This is called the profit inequality because the gambler is doing as well as a prophet is doing. A prophet who knows the future would just take the best prize, right? We don't know the future, so we're stuck playing some strategy. So this is saying that the gambler, with his simple strategy, is actually doing as well as a prophet. I mean, as well as a factor of 2 of a prophet. Okay? So let's discuss this solution. This is simple. I need one number. Great. I claim it's pretty conclusive. It says clearly you're trading off something. You are trading off the probability you don't stop ever and get nothing with the probability you stop with a price that's not too good, right? There's a later thing coming, price coming later that's better. And you trade those probabilities off at exactly 1/2. And that gives us something okay. It's very robust. What if I change the order of prizes? That doesn't change the threshold I used. And therefore, it doesn't change this guarantee at all. The maximum is the same, and so I still get a factor of 2. Okay, so the bound I get if I make changes to my game doesn't change at all. Okay, so I could change the order, or I could change subtly change the distribution above the threshold I pick or below the threshold I pick. Nothing would change. Okay, and it's actually going to be a very general theorem that I'm going to use later to apply to some problems in mechanism design. And the reason why it's so general is because as you see the proof of this theorem, is it's not going to matter. It's going to be invariant to what I call the tie-breaking rule. Okay, and the tie-breaking rule is the following. Suppose there are multiple prizes above the threshold. Which one does the gambler get? Well, he gets the first one that he comes to, right? That's our tie-breaking rule. If there are multiple prizes above the threshold, he gets the first one. So lexicographical is the gambler's tie-breaking rule. We're going to apply this same theorem in cases where we're doing tie-breaking in a different way. And since the theorem doesn't need the tie-breaking rule, it's going to have the same, we're just going to plug in the theorem as a black box. Okay? Good. So I'm now going to prove this theorem. This is going to be the most strenuous proof that I'm going to do in the talk, and it's actually very, very easy. Okay? So let's let Qi be the probability that a prize is below the threshold. Prize I is below the threshold. So the probability the gambler never stops, we'll call that X. That is just the product of the Qi. It's the probability that every single prize is below the threshold. Then we never stop. Okay, so my strategy is to get an upper bound on the expected maximum prize, get a lower bound on the prize the gambler gets, and then plug in X equals 1/2, which is what I said a good threshold was, and to prove the theorem. So that's what I'm going to do. Okay, so to start off, the expected max is less than or equal to t plus the expected maximum positive amount of a prize above the threshold. Okay, so let's look at 2 cases. Let's assume that the best prize is below the threshold. Then this is clearly an upper bound on the maximum prize in that case, when the best prize is below the threshold. Okay, and now let's suppose the best prize is above the threshold. The highest prize is above the threshold. Well, then I get t plus the difference between the best prize and t. And that's what this is. So this is exactly equal in the case where, in the second case, and it's an upper bound in the first case, therefore it's an upper bound in general. Okay, expectations of maximums are a pain, so I'm going to replace it with an expected sum. Because the sum of the expectations is always bigger than the expected max. Good. Okay, now I'm ready to go for my lower bound. Okay, so what is the gambler getting? Well, if he stops, which happens with probability 1 minus x, right? The probability there's a prize above the threshold, then he stops. Then he gets at least t, right? Because that prize is value above t, so he gets t in that case. But he's also going to get the additional value above the threshold of whatever that price happens to be. But that's kind of a pain to figure out. So I'm going to make not keep track of all of the extra value that he gets. I'm going to only look at the expected value he gets above t when there's exactly one prize above t. Okay, so if there's more than one prize above the threshold, I'm going to assume he just gets the threshold. Okay, and if there's exactly one, then he gets the prize. Okay, and so this is where I say it's sort of invariant to the tie-breaking rule, because here the tie-breaking rule wouldn't matter. If there's only one thing, then I'm talking about what I'm getting, and if there's multiple things, I just get at least t. Okay, so good. Let's write out what I mean, the expected prize if there's only one prize above t. So I sum over all prizes, the expected positive part of that prize above t, conditioned on all other prizes being less than t, times the probability that all other prizes are less than t. And I sum that over all I. Okay, so now let's simplify this second part of the equation. So this is, of course, just the product of all qj not equal to I. But that's going to be bigger than x, because x additionally has a qi multiplied by it, and qi is less than or equal to 1. Right? Good, so I'm just going to factor this x out of the whole thing. And now let's look at this expectation. I have the expectation of some random variable, and I'm conditioning on something that's based on other random variables, not the random variable I'm talking about, so I can drop the conditioning. Okay, so I have this equation. And now I want you to compare this equation to that equation and note what happens if I plug in x equals 1/2. Okay, we're good. Any questions? That's the hardest proof we're going to do. Good. I give this talk to economists, and for economists I have to explain to them why I care about two approximations. For this audience I probably don't have to explain it, but I think it's useful to remember, because if you have to talk to economists you want to tell them why we care. Okay? And remember one of my goals. My goals was conclusive understanding of what's important for mechanism design. Okay? And constant approximations help me identify what are the salient features from the sort of details or the unimportant things. If I want true optimal, I have to pay attention to everything. Right? But so can I do okay not paying attention to everything? And the things that I have to pay attention to get a good approximation are the important things. The things I don't have to pay attention to aren't the important things. And so this lets you determine what in the model is important, or what in the kinds of mechanisms you're considering is important for doing a good job. Okay? So in other words, I can say, is X important for mechanism design? And if there's no mechanism without X that's a constant approximation, no if there's a mechanism without X that's a constant approximation. If I can get a good mechanism without taking into account X, then X is not important. If I can't get a good mechanism without taking into account X, then X is very important. I better think about it. So I want to give two examples that come from mechanism design here. So one is competition between agents. So usually you think of mechanism design, you're like running auctions, agents are competing for stuff, whatever. Is competition important? My answer is no. I can get constant approximations without competition. Okay, we're going to see that later. Are transfers important? Let's suppose I want to maximize social welfare. I have an item, I want to give it to a bunch of, say, n players. If I can't charge players money, then I have to just give it to a random player. And what if there's only one good player and everyone else is bad? Then I'm getting like a linear approximation. Right? Without transfers, I'm in big trouble. Transfers are very important for mechanism design. Competition is not so important. Yes, sir?
So, a lot of times you can look at some of the algorithms you design for mechanism design. The transfers is coming from a dual to an LP. Right? And so, in essence, this is sort of an oblivious algorithm in the sense that, it doesn't actually depend on, the orderings of these different distributions. Is the reason you're able to avoid transfers that it's not using sort of the dual and you don't have to create compensation between two different players?
I'll tell you the answer. The answer is, the Competition, you said. Why don't I care about competition?
No, I mean, it's
I do
from
care
like
about
a transfer standpoint in the sense that, you can take like, min-cost sort of flows, and the way that you create the dual is you create this other sort of payment scheme, which then, makes every edge sort of fair, right? And there are ways to interpret this in mechanism design for some useful ends, right? So here, the optimal sort of solution for this, stopping problem, one could write it based on an LP, and then sort of the dual would come, you might be able to interpret it as being a transfer. Is there any sense in which, because you're not solving this problem optimally, because you're not worrying about the dual, that's why you're able to get around transfers?
I'm not getting around transfers.
Okay, it's just
I said
range.
without transfers, I'm in big trouble.
Oh, okay. All right.
I said without transfers, I can't get better than an N approximation. Transfers are very important for mechanism design.
Okay.
Competition, I said, wasn't important.
Okay.
Okay, and I'll tell you why competition is not.
In transfer, you are taking people with varied valuation. But when the example of the competition, if people have varied valuation, then how do you get constant factor? You have to figure out who has the highest valuation. So how do you get constant factor? Unless you assume that everybody has the same Bayesian distribution.
No, we'll see. We'll see. I mean, this is a conclusion of the talk. The competition is not so important, and I want to compare that to transfers, that are obviously important. Okay, so it shouldn't be obvious why competition is not important right now, and we'll see. Okay, so let's see. Yes.
There seems to be an implicit assumption that the constant factor is not too large, like you don't lose 1 billion to 1.
So that's important if I want to actually tell someone how to design a mechanism, right? And I just said I want to understand what's important. And I argue that constant approximation gives me a good lens on what's important and what's not important, even if that constant is 1 billion. Now, I don't know of any settings where you get a constant approximation in mechanism design settings and it's 1 billion. Okay, I know of no such settings. The constants I know of are between 2 and 10 for tight analyses. Okay, and so I don't know of anything that's not in that small range. But you might argue that 10 is too big. Okay, and I agree. 10 is too big. The point, though, is that the mechanism from theory that gets the constant approximation isn't the end of the day. The point of that mechanism was to identify what was important, and those are the things you pay attention to first. And then if you're designing a mechanism in a real scenario, you add some sort of, maybe ad hoc improvement over it to do better in the real life scenario you actually are dealing with. Okay? But I want to know what's important first, and that's what I hope theory does. And then there's some applied theory which is going to tell me how to actually use this theory in real life to get the last end of get the rest of the way there to a good solution. Okay? Good. So here's an overview of the things I want to talk about today. I'm going to talk about, basically this is going to be a talk by example. I'm going to show you a number of examples of constant approximation telling you lots of interesting things about mechanism design. And they're going to be in fairly different scenarios. Okay, so the first scenario I want to talk about is in single dimensional mechanism design. Okay, so single dimensional mechanism design is like you have one item to sell and each player has a single dimensional value for that one item, right? So it's single dimensional. Multi-dimensional, the next thing I want to talk about is multi-dimensional mechanism design. So there might be multiple items for sale. You have a different value for each item, and that different value is, of course, a multi-dimensional object, which is specifying your preferences. And the last thing, which we may get to if we have time, is prior independent settings. So the first two take the standard economics approach of assuming the designer knows the distribution from which the agent's preferences are drawn. And the last approach does a more computer science-y kind of thing. We're saying, what if we don't know anything? Can we design one mechanism that's going to be good in many scenarios? Okay, and what I think is really nice and important about the work that computer scientists are doing in mechanism design is that economists think they've solved this problem. and they their solutions are fantastic and give really good intuition. And we're going to hopefully add to that with approximation. But there aren't good solutions for these two problems coming from economics. So we're able to say something where there isn't really a nice story in existence at all. Okay, I'm going to focus here on profit maximization, meaning I think of the mechanism designer as a seller, and he wants to make the most money. Okay, and I want to point out that that is an example of an objective, and everything that I talk about can be thought about for other objectives as well. It's important to talk about an objective that's not social welfare, though, because social welfare has some special coincidences that make it a little bit too easy. Okay, so this is the more general objective to talk about.
So just one comment, returning to what Alexandra said in the beginning, that even in the first model question, you mentioned if the solutions are changing in time, often expected maximum is not a good objective. So the expectation is not a good objective, as St. Petersburg paradox is one where you can get the expectation is large because some of the distributions have big tails, so there are some very unlikely events that might happen and contribute a lot to the distribution, to the expectation. But if you want to devise a strategy, you might, that might not be the objective. You might have a concrete utility function that you're applying for the chaos. So that's.
And I'm going to take non-linear utility functions and punt them because if you're so. They present a lot of problems, and the problem in mechanism design, you can often trade off risk between players. And if you start with utility functions that have some form of risk, like they're not risk neutral, then trading off the risk between players allows you to gain more revenue, say, and that is a little bit troublesome. And so it really changes the question. And so I don't want to really change the question, so I'm not going to deal with that. Okay? So all I want to say is if you have non-linear utility, then it completely changes the kind of questions you're asking, and you're in another area of work. Okay? Okay, so I want to talk about single-dimensional Bayesian mechanism design. And so the example problem I have is the following. There's a single item for sale. There are n buyers. The distribution for each buyer's value is drawn from a product distribution. So player I has distribution Fi, and these are independent draws. Okay? And my question is come up with an auction that has the highest expected revenue. That's my question. Okay? So as I'm going to do in this talk, I'm going to talk about what's optimal, and then I'm going to talk about approximation to that and say why I like the approximations better. Good. To talk about what's optimal here, I could spend an hour, but I'm going to spend 2 minutes instead. There's a really fantastic theory due to Roger Myerson, and it's quite fantastic. His paper is brilliant and worth reading by everybody, but I'm going to do it in 2 minutes. Okay, so we start with the following statement that so I want to know what I can design in equilibrium. What can be an equilibrium of a mechanism? So I can have what's called a Bayes-Nash equilibrium if and only if the allocation rule in equilibrium is monotone, meaning it must be that someone, if I take an agent and compare what happens to them in two cases, the case where they have a low value and the case where they have a high value, they must be more likely to win when they have a high value in the equilibrium. Otherwise, the high value could pretend to be the low value following the strategy of the low value, and that's not an equilibrium then, right? So the equilibrium must have this monotonicity property. Good. Let's talk about revenue, because our objective is going to be profit. Okay? So I want to define the following revenue curve. Think about taking a single agent I. Okay? Agent I's value is drawn from a distribution. So I want to think of the revenue I get as a function of the probability at which I sell to them. Now it's much easier to think about the revenue I get as a function of the price I offer them. Right? If I offer them a price of $10, then they buy with probability, the probability their value is above $10, right? And so I get 10 times the probability they're above 10, which is 1 minus capital F of 10, right? Where F is a distribution function. Okay, so I'm going to actually write that in terms of the probability they buy instead of the price they buy. Okay, so Q is the probability they buy, which is the, right? And so F inverse of 1 minus Q is the price I would have had to offer them so that they buy with probability Q. Okay, so this gives me a revenue as a function of Q, the probability I sell to the guy. Okay, and so I've illustrated one such revenue curve. Q goes from 0 to 1 because I have probably 0, probably 1. I could sell to this guy. That's a revenue curve. Okay, I'm going to define the virtual value of a player to be this formula. Ignore the formula. This is the derivative of the revenue. Okay? And if you've had Economics 101, you know that to maximize revenue, you should maximize the derivative of the revenue, right? You set those equal, and that's going to be maximizing revenue. If you haven't, that's OK. That's what you do. OK, so this virtual value is the marginal revenue. You want to maximize the derivative of the virtual value. OK, so I'm going to call the virtual surplus to be the virtual value of the person who wins the auction. And the theorem then is that virtual value is equal to revenue. Okay, so now I want to, knowing that virtual value is equal to revenue, I now say, well, I need to somehow maximize virtual value subject to monotonicity, right? To be in equilibrium, it's better to be monotone. And my objective revenue is equal to its virtual value. So the way to think about this is the following. Actually, let me add one more point. Okay, I'll call the distribution Fi regular if and only if the revenue curve is concave, which is the same thing as the virtual values being monotone because the virtual values are the derivative of the revenue curve, and concavity of the revenue curve implies monotonicity of the virtual values. Okay? So let's assume we have a regular distributions. Okay? And I want to maximize revenue subject to monotonicity. So here's how I'm going to do it. Forget monotonicity. Just maximize virtual surplus. And then let's hope that it's monotone. Okay? And if it happens to be monotone by luck, then we're done. Okay? So, well, if virtual values are regular, then so if the distribution is regular, then these virtual values are monotone. That means an agent with a higher value has higher virtual value. So if I just tried to maximize virtual value, meaning give the item to the agent with the highest positive virtual value, that's going to be a monotone rule, because if they were winning with some value, with some virtual value, if they increase their value, they get a higher virtual value, so they still win. So it's monotone. Okay, so the theorem is this. For regular distributions, the optimal auction sells to the bidder with the highest positive virtual value. That's true because revenue is equal to expected revenue is equal to expected virtual surplus, and this rule is monotone, which is what I needed for it to be possible in equilibrium. Okay, and there's a nice corollary of this statement, which is what happens in the IID case if the bidders are drawn from the same distribution. Then these virtual value functions are the same for every bidder, right? Virtual value function is the same for every bidder. So the bidder with the highest virtual value is also the bidder with the highest value. And the condition that their virtual value has to be at least 0 means their value has to be at least the inverse virtual value of 0. Right? So the bidder with the highest positive value. So for IID regular distributions, the optimal auction sells to the highest bidder, subject to the constraint that their bidder is at least the inverse virtual value of 0. And this auction is actually otherwise known as the Vickery auction with a reserve price of the inverse virtual value of 0. Meaning You have a reserve price of that inverse virtual value, and you sell to the bidder with the highest value above that. That's it. Okay, so that's my, maybe it was 5 minutes, review of optimal auction design. And for the purpose of this talk, you don't have to understand all of this. That's fine. What you should understand is that revenue is given by optimizing these virtual value functions. So basically, there's a mapping from values to virtual values, and you optimize that, and then you're optimizing revenue. Okay? That's what you should understand. Okay, so what are optimal auctions? Let's review from the last slide. For IID regular distributions, the optimal auction is victory with reserve price. It's a very natural, simple auction. Like the eBay auction is a victory auction with a reserve price. You can post a minimum bid, and the person who bids the most above that wins. That's a victory auction with a reserve price, essentially. So these are very natural. They happen all the time. In general, it's sell to the bidder with the highest positive virtual value. Okay, what does that mean? It's complicated, very dependent on the distribution. So this IID regular case, it seems like it's kind of special. And the question is are the settings people run auctions in always going to be IID and regular? Probably not. Right? They're probably more general. This general case, we know what the optimal auction is, but no one really runs it. They instead run the auction that works in the IID regular case, but it's not optimal in the general case. Okay, so the state is that basically we know what's optimal, and the optimal thing is too complicated. And so people run the thing that's not optimal, even in the case where they should be running some more complicated thing. Okay, that's the status of the state of things. But so that motivates a question, which I want to answer now, which is, well, we're running these reserve price mechanisms even in settings where they're not optimal. So are they close to optimal? Okay, so let's answer that question. Here's the theorem that answers that question. The theorem is that the victory auction with a constant virtual price, where the probability that the item remains unsold is 1/2, is a 2 approximation. And that theorem statement should look kind of familiar. And the proof of it is the following. I'm going to apply profit inequalities to virtual values and use a tie-breaking rule, tie-break by value. So what do I mean? I want to maximize the virtual value of the winner, because maximizing the virtual value of the winner is equal to maximizing my profit. I'm going to impose a reserve price in virtual value space, so a constant threshold in virtual value space, which is a constant virtual price, okay, such that the probability there's only that no one wants to buy anything is exactly 1/2. And then what is the victory auction with a bunch of reserve prices? Well, if you make your reserve price, then you win. Otherwise, you don't win. If you make your reserve price, then we take the highest value, and that person wins. So subject to making your reserve price, we break ties by the highest value. Okay, so the person with the highest value wins. Okay, so let's be more specific here. So profit inequality, we had prizes, we had a threshold, we had a maximum prize we wanted to get, and we had the prize for threshold T. Okay, when I'm talking about the victory auction with reserve prices, what do I have? So I'm going to analyze everything in virtual value space. So I want to maximize, I have virtual values of for each of the coordinates. And I'm going to post a single virtual price. Okay? I'd like to approximate the optimal revenue, which is the maximum positive virtual value. But instead, I get the victory revenue with the reserve price. Okay? So
don't you need to know the number of bidders now to have probability of no sale equal to half?
Absolutely.
So
and in the original gambler's game, I knew how many days I was playing.
You also have another distribution.
And I have another distribution.
In practice, let's say you have some number of people coming, even if it's a simple setting.
That's not my theorem. My theorem is you know the distributions.
No, but in something, I'm saying it's not a satisfactory theorem for such a scenario because it's not robust. You need to know the number of people to...
You also have to know the exact distributions of the people.
Yes. Let's say even if I know that people have similar distribution, then Myerson will anyway will give me a constant number. But if I need to apply this theorem, I need to know the exact number of people.
Can't you do something in the case, so suppose all the distributions were the same and you just didn't know the number of people. Could you get a constant factor in that case?
Absolutely.
Just by using like a doubling sort of trick?
It's easy.
Then the Myerson will give you the optimal will be a single price anyway.
So
when you apply this theorem, you need to know.
So I'm going to have some discussion of this, and I'm not going to discuss at this point. I'm not too concerned by this issue, though. So let's discuss and complain about this solution. Okay, it gives me a 2 approximation. You do have to know the distributions completely, and that's, I believe, a more serious condition to knowing the number of bidders. You have to know actually their exact distributions, right? That's a more serious complaint. A constant virtual price actually gives me different actual prices, right? Because if the distributions are different, I invert the constant virtual price and I get a different actual price. So now I'm talking about running an auction with a different price for each player. That seems already kind of not very good, okay? It is simple though, because if you have the distributions, coming up with these virtual prices is fairly simple. It is robust in the sense that, in the following sense, if you had collusion, it wouldn't change anything, right? Because an arbitrary tie-breaking rule works. And what is collusion? Collusion is, I might lower my bid so that you win when we're both competing against each other. But actually, I don't care. If there are more people above the threshold, I don't care which one wins, right? And I'm happy if he just pays his threshold, right? So the result I get, since it doesn't care about tie-breaking, doesn't care about things like collusion and such. Okay, and good. So forget even doing Vickery. Just post these prices, and people come in whatever order they want and take the prize if they want it, and first come, first serve. Right? That also satisfies the same theorem because you just break ties a different way.
Each one has his own price.
Each one has its own price. That's fine. I complained about it already. Okay. Good. So let's talk about competition. Competition didn't matter, right? Because the fact that other people they're not driving the price up. I can put people in any order, and the first person who wants to buy in this worst possible order buys, right? And this theorem still says they get a 2 approximation. So I get a 2 approximation without any competition.
So it's because you have priors. The first person who buys, but then he just pays the reserve price.
That's the point. The point is I'm happy just getting the reserve price from any of the bidders who are above the reserve price.
But you have already included the competition when you are satisfying that inequality, probability no sale equal to half.
Yes, but I'm not actually looking at the bidders to satisfy that equality. I use my knowledge of the distribution instead. In other words, with my knowledge of the distribution, I can sort of...
Competition then? What does competition mean?
What does competition mean?
Yeah.
I have 2 bidders in an auction, they compete with each other. Okay? It's not competition if I have some other bidder in mind who might be there or might not be there, and I just set your price higher. That's not competition. That is me thinking about and setting a higher price for you. So my point, the obvious point here is that, yes, you can simulate competition by raising prices. And that is what's happening here. You're simulating competition. And so there actually isn't any real competition happening.
Because if you think that there will be another person to satisfy that probability no sale, you will increase everybody's price. Why won't you do? Because that inequality will force you to raise the prices.
It depends on whether the bidders are actually there or whether the designer just thinks they're there. Right? This says the designer has some distributions for what bidders are showing up, and he sets prices. The bidders that actually show up are not competing with each other. The bound is guaranteed regardless of whether they compete with each other or not. They're not driving the price up at all.
The theorem is guaranteed if you have those distributions showing up. If those distributions don't show up, you are saying the theorem is still true?
I'm saying if
you need those people with that distribution coming up to you.
I do need this. Distribution is true if the bidders' values come from distribution. However, if those bidders choose not to compete with each other, it's still fine. I still get the bound. Okay? But let's address some of these complaints. Okay. One big problem was these prices I came up with depended. They were different for each bidder. That was annoying, right? They depend specifically about the distribution. That's unavoidable. So here's a question you might ask second, which is, can you get a good approximation with anonymous reserve pricing? Meaning, and this is the mechanism that worked well in the IID regular case. Okay, in the IID regular case, anonymous reserve pricing is great. In the non-IID regular case, for instance, that's not optimal. I just gave you on the previous slide a 2 approximation to it, but it uses different reserve price. That was a pain. So what about an anonymous reserve price? Okay, so here's a theorem. You can get a 4 approximation. The proof of this theorem is by a more complicated usage of profit inequalities, but it's profit inequalities nonetheless. Okay, I'm not going to give you the proof. It's just a profit inequality kind of proof. Good. The bound isn't tight. I believe the answer is 2. I haven't been able to prove it. I'm kind of embarrassed about it, so don't tell anyone. I believe this theorem justifies the wide prevalence of the anonymous reserve prices. Let's suppose anonymous reserve prices were often bad, like really bad. Well then, people might be using other auctions, right? But this shows that actually, no matter what, using a single reserve price is as good as some much more complicated thing. Okay?
How
good.
bad can it be in the non-regular case?
Logarithmic. Okay, so you can generalize these results beyond single item auctions. And I have one statement that I want to make about that, which is that if you have non-identical distributions, possibly irregular, then oftentimes posted pricing mechanisms where I come up with a different price for each player, let them arrive in any order they want, then oftentimes this gets a good approximation to the optimal revenue I could have gotten from having them all there at once in one mechanism and running some complicated Meyerson-like procedure with virtual values. Okay? So this says you don't have to have everyone all at once. You don't have to have them competing with each other. You can just post prices. You can find prices that are good enough, even with strange feasibility constraints, et cetera. And the general proof of this kind of approach is that, well, the optimal mechanism, we know what it is. It's maximize virtual surplus. It's maximize the derivative of the revenue curves. And then you show that reserve pricing mechanisms are virtual surplus approximators. Okay? I think the biggest challenge area from this line of work is addressing non-downward closed settings, or settings where you have to sell to people with negative virtual values. And this theorem only applies in downward closed settings. A downward closed setting is one where if I have some set of winners, I can just reject some people, and that's fine. So any subset of a feasible set is feasible. And that means I would never sell to a bidder with negative virtual value, because I'd always at least post a reserve price of the inverse virtual value of 0. So I'd never sell to a bidder with negative virtual value. So if you have non-downward closed settings, it might be worthwhile to sell to someone with negative virtual value so that you can also sell to someone with really high positive virtual value. And so these kinds of settings we don't know how to analyze at all. Okay? So that's the single-dimensional setting. I want to now move on and talk about the multi-dimensional setting. And so the example I want you to think about is this simple multi-dimensional pricing problem. I have a single unit demand customer, meaning there are a bunch of items available and they want to buy at most one item. So it's like you want to buy a house, there are a bunch of houses available, you want one of them. Okay? Your value for each house may be different, and I'm going to draw them at random from a known distribution. Okay? I would like to put prices on these houses to maximize the revenue I get as a seller when a buyer draws his value from the distribution and takes his favorite house, meaning the house whose value minus price is the highest. Okay, so what's optimal?
Wait, there's one seller who has all these n houses?
There's one seller with all these n houses, and one buyer who wants a house whose value is drawn from distribution. Good. So how do I optimize this? Well, I can take my distribution, my feasibility constraints, and my incentive constraints and throw them into my favorite solver and push the solve button and hope some answer comes out. In some cases, this is polynomial time. But I still don't find it a very useful, conclusive solution, even if it is polynomial time, because I haven't understood the problem at all. Okay, so there's little conceptual insight. Some cases it's polynomial time, most cases it's not. So that's problematic, so I want to approximate it. The first thing you have to deal with when trying to do approximation is I want to approximate something and I don't understand what that optimal thing is. And so we need to get an upper bound that we do understand. So I want to compare two problems. One is this unit demand pricing problem, which I just mentioned. And the other is the auction problem we talked about for the first 30 minutes of this talk. Okay? And I want to ask you, if the distributions are the same, which seller would you rather be? Would you rather be the seller of the auction, running the optimal auction where we know what it is? It's Meyerson's, maximized virtual set for us. Or would you rather be the person who has to post prices on these houses and the bidder takes their favorite, the single buyer takes the house that maximizes the value minus price? Okay, so they have the same informational structure, so I can ask this question. It's an apples to apples comparison. The theorem is that I'd actually rather be the auctioneer. And what's the intuition for this? The intuition for this is actually having these bidders compete with each other drives the price up, and that should help my revenue. And so you can actually take any pricing here and design an auction around that pricing that uses the competition to get more money. Okay? And so that then allows me to get the following theorem. If I post prices on these houses with a constant virtual price, such that the probability that the person doesn't buy any of my houses is exactly 1/2, then I get a 2 approximation to this, which is an upper bound on that. Okay? How does this work? Well, it's a profit inequality. And we break ties with the agent's utility function. They're choosing the house to maximize VI minus PI. So we're breaking ties that way. And the same proof as before. Okay? So that was a case where I had just one agent. And I want to generalize this to talk about more agents where there's actually contention for the houses, etc. And that's actually easy to do. So in many unit demand settings, I can come up with what I call sequential posted pricings, which are the following. I come up with prices for each agent and each house, say, and then I allow the agents to arrive in any order and take whichever their favorite house is while supplies last. And worst case over orders, this gives me a good approximation. Okay, and I want to sort of give you the high-level approach for proving these kinds of theorems. The first step is to make an analogy to a single-dimensional setting, kind of like we did on the last slide. So I'm going to take each multi-dimensional agent and turn them into a bunch of single-dimensional agents that then compete with each other. Okay? I then want to say this single-dimensional auction problem is going to have more revenue than the multi-dimensional pricing problem. Why? Because competition increases revenue in the single-dimensional auction problem. Okay, and that's a theorem. Then I want to say that if I'm posting prices, that actually multi-dimensional price posting gives me more revenue than single-dimensional price posting. Why is that? Well, when I'm posting prices, I'm not using competition. So I shouldn't think that there's really a big advantage of being in the single-dimensional setting over the multi-dimensional setting. So I'm not using any competition in posting prices. So that's one thing. And in my definition of sequential posted pricing, I said there's an adversarial order. And there are less orders in the multi-dimensional problem than in the single-dimensional problem. In the single-dimensional problem, I could order all agent item pairs. And the multi-dimensional problem, I can only order each agent, which means all of the items come together for that one agent. So there are fewer orders to worst case over here. Okay? And then I have to instantiate this reduction by showing that I can come up with a single-dimensional pricing that is a constant approximation to the single-dimensional auction. And this is an easy question to answer because this is in a single-dimensional setting, and we understand single-dimensional settings completely. We know what this is. This is maximized virtual surplus. And these are just, we need to show that they're virtual surplus approximators. Okay? And that's, we've already, by example, in the previous part of the talk, shown how to do that in some settings, and so I'm not going to do it anymore. Okay, that's sort of the high-level sketch of how you show these kinds of results. Okay, so some discussion. The mechanisms you get out of this are very robust in the sense that they don't depend on agent ordering, they're posted pricings, they don't depend on collusion, they don't depend on a lot. It's conclusive in the sense that it shows you very strongly that competition is not that important for approximation. I was able to take a setting with competition and turn it into a setting where I just post prices and people come in whatever worst case order they want, so no one's competing with each other in those settings. And this close connection between unit demand preferences and single dimensional preferences means that somehow the unit demand incentives are very similar kinds of incentives to single dimensional incentives. Okay? And so that's I think a nice intuition. Posted pricings are very widely prevalent. If you look at eBay, eBay is migrating their auction platform to posted pricings with their buy it now feature. Furthermore, pretty much most things everyone buys is sold with posted pricing, right? And so it's a really nice, I think it's a nice, this corroborates like the practice of selling stuff, which people actually mostly use posted prices. And the fact that that's not too bad is relieving, right? Because if it was bad to use posted pricing, people would be having a lot more dynamic mechanisms, and you go to the grocery store, you have to bid for your lettuce. And that'd be really annoying. So it's nice that these posted pricings are good approximations. I have one comment, which is that the role of randomization here is very important. In all the theorems I discussed in the past, I was assuming deterministic mechanisms and comparing a deterministic posted pricing to a deterministic optimal pricing, for instance. Randomization makes the problem very, very interesting, and here are two papers which discuss that in more detail, which I'm not going to talk about. I think the biggest open question in the area of multidimensional mechanism design is getting beyond this unit demand assumption. So when agents are unit demand, I have an agent who wants one of many houses. Then unit demand incentives are very similar to single dimensional incentives. And I have this nice upper bound from the single dimensional representative problem. In beyond unit demand, I don't know of anything good. I don't know of a good upper bound. I don't know of a good way of understanding incentives. Okay, so I think that's the most interesting and important open question. Good. So so part 3. When did I start? 3:30. So I've gone for an hour and a half. So why don't we stop and not do part 3?
Are there any more questions?
Yes.
You mentioned postal pricing being prevalent, mainly for small purchases, but have you bought a car or a house recently?
Sure. And so those are, so you're saying those are negotiations.
Lots of stuff.
And the question is, to what extent do these negotiations approximate an auction versus what extent do they approximate a posted pricing, right? And for instance, buying a car, if you're buying a car from a dealer, he's not thinking, oh, if you don't buy, I mean, he's not like putting your bid against someone else's bid, which would be an auction. He has some price in mind which he's willing to negotiate to, and you either will sell above it or not, right? Houses are a little bit different. Houses usually negotiate, and there are sometimes other bidders. In the current market, actually, there probably aren't that many other bidders. So it's basically a posted pricing, and they've agreed on a price. They have a price in their mind before, and they're not going to go below. Or maybe you're a good negotiator, and you get. I mean, essentially, it's a posted price, is what I'm saying. Okay.